Okay, in a previous example, we defined what we meant by the determinant of a 2 by 2 matrix, and what we'd like to do is see if we can extend our definition to matrices that have larger dimensions. Okay, we are still looking at page 87 here in the workbook. Okay, and this is a definition near the bottom of the page, and it's going to lead us into a method for finding the determinant of a 3 by 3 matrix or a larger square matrix. All right, so the first part of this definition, notice we're starting with an n by n matrix. Aij is notation that we've already used just to represent an entry in the matrix that's in the ith row and the jth column, so nothing new there. What is new is the second piece, A tilde ij. That actually represents a matrix that's smaller than the one that we started with, and in particular, it's the matrix that we get by deleting the ith row and the jth column of A. Kind of a strange definition to make, but it's going to turn out to be a key in calculating determinants of larger matrices. All right, so just to get comfortable with this notation, let's look at example 2 here together. Okay, and they ask us to calculate some matrix entries and some tilde matrices, basically. Okay, and we'll start with the first two here, A11 and A11 tilde. Okay, so A11, that's just asking us for the entry in the first row and the first column of our matrix. Okay, so that would be the number 1 up there. All right, whereas A11 tilde, that is a matrix that we get by crossing out the first row and the first column of our matrix. Okay, let's illustrate that. So if we cross out the first row and the first column, notice that what's left is this 2 by 2 matrix 1, 2, 4, negative 2. Okay, that's what we mean by A11. All right, let's get rid of what we wrote so that we can go on to the next phase here. Okay, and now let's see if we can calculate A21 and A21 tilde just in an analogous way. Okay, so starting with A21, that is the entry in our matrix that's in the second row and the first column. Okay, so that would be that one right there. Okay, and then the matrix, A21 tilde, would be the 2 by 2 matrix that we get by crossing out the row and the column that 0 is in. Okay, the second row and the first column. And you can kind of see what's left there. Okay, a 2 by 2 matrix that looks like 2, negative 3, 4, negative 2. Okay. And finally, let's look at A23 and A23 tilde. Same idea. This time we're looking for the entry that's in the second row and the third column. Okay, so we'd be talking about this entry, 2. Okay, and now to get A23 tilde, we're just going to cross out everything in the row and the column of that entry, just like we did before. Okay, and so this time we are going to get, we can see the terms that are left over are 1, 2, 1, 4. Okay, so again, kind of a strange definition, but it's going to turn out to give us a way to calculate and define the determinant of matrices that are larger than 2 by 2. Okay, so let's move on then to the definition on the next page. Okay, and we'll kind of see how some of that notation comes into it. Now, just to warn you, this definition has a lot of terms in it and a lot of notation, and so when you look at this the first time, it might not make a whole lot of sense. It's kind of out of context, so that's okay. Don't feel bad if part of this sort of sails over your head the first time that you see it. I'm going to spend a minute just to talk through it, and then I think that it will make more sense for all of us when we do some examples later on. Okay, so this definition on page 88 gives us a way of defining determinants recursively for larger matrices. Okay, and specifically, we have the determinant of A being defined as this big, long sum that you see here. Okay, let's just look at the pieces kind of one at a time here. So there's a negative 1 to the 1 plus j. That's basically just going to be either plus or minus 1 depending on what the power is. There's a1j, that's just an entry from our matrix. And then there's going to be the determinant of one of those tilde matrices that we talked about a minute ago. Okay, I like to call this formula, or one way to visualize this formula is it's really expansion along the first row of our matrix. Why do we call it that? Okay, well, it really has to do with kind of looking at what's going on here with the 1j that I just circled. Okay, the 1 is basically giving us the row that we're in, and the j is giving us the column, and because the 1 stays constant, as we add up this sum from 1 to n, we're staying in the first row. Okay, every entry there is in the first row. The j, on the other hand, changes. It goes from 1 to n, and so as we go a11, a12, a13, we're kind of moving along the first row of our matrix term by term. Okay, and like I say, we'll see an example of that in just a minute here. Okay, what's interesting about a determinant is there's nothing special about the first row. We could have chosen any row, or in fact any column, and we would come up with the same thing. All right, so if you look a little bit down here to the first formula below the note, it gives us another way of calculating the determinant. And notice that that formula looks almost the same as the one above it, up here. Whoops, sorry. The only difference is that instead of having a 1, we have an I, which means that we're really expanding along the ith row. Of our matrix. Turns out that if we do that for a specific matrix, do all the arithmetic, we'll get the same answer that we did in the formula above. And then the very last formula, same idea. The only thing that's changed here is that instead of j going from 1 to n, we've got I going from 1 to n. If you think about it, this is actually an expansion along the jth column. And our claim is that no matter which of those formulas we use, we're going to get the same number, and that number is what we're going to call the determinant. Okay, and in future examples, we'll actually use that with a specific